morning, professors. The topic of our project is M puzzle and innovation. Here is an M puzzle, the H3P puzzle with 3 columns and 3 rows. And here is its solution. Today, we are asking 2 questions. The first one is, without taking the pieces away from the frame, that is, using legal operations, can the left be rearranged to give the right? And the second is, if so, how can it be rearranged? Technically speaking, can we use legal operations to solve the left puzzle? And if so, how can it be solved? And in this presentation, we are mainly focusing on the blank square, and we use the movement of the blank square to represent the movements and the operations. Now, let's answer the second question first, because we can assume the puzzle is solvable, and we try to solve it. Basically, we can solve the puzzle row by row. We can solve the first row first, and then the second, and last the third. But if we use the row by row algorithm and try to solve the 15 puzzles, which have 4 rows and 4 columns, we have difficulty in solving the last row. And therefore, but this is not encountered when we solve the H3P puzzles, the one we encountered just now. Therefore, we have to introduce another algorithm called the L algorithm, which for short we denote it by LA, and we change the solving order. If we use LA to solve the 15 puzzles, we solve in this way. And then first, we solve the first L, and the second, and then last, the third. And by having our L algorithm, we can generalize this result to all MPQ puzzles, rectangular as well. And this is a forever successful algorithm for all solvable puzzles. Now, we answer the first question. Is a certain given puzzle solvable? For simplicity, we introduce the concept of alignments. And for example, for these 8 puzzles, we write the alignments like this. 1, 2, 3, 4, 5, 4, 7, and then X, 6, 5, like this. And we introduce some notations. We use the NA plus to denote the set of all solvable alignments, and A minus for unsolvable ones. And therefore, any alignment alpha is an element of either A plus or else A minus. So we go to look into the 3-2-2 puzzles first, and we write all the alignments of 3-2-2 puzzles, and we write it like this. And then, for example, 1, 2, 3 is the solution alignment, the solution of the 3-2-2 puzzles, and by using legal operations, we can get 2, 3, 1, and we call this property of using legal operations to transfer from one alignment to another. We call it congruence. And if those puzzles like this, 1, 3, 2, which cannot be rearranged to 1, 2, 3 using only legal operations, we call 1, 2, 3 and 1, 3, 2 non-congruent. And we use dark circle to represent congruence and hollow circle to represent non-congruence. And therefore, the alignments in each column is congruent. To generalize the results from 3-2-2 puzzles to all MPQ puzzles, we introduce a concept called fusion. And we use the plus sign to denote it. For example, if we fuse 1, 4 with 2, 3, 5, then we obtain a result 1, 4, 2, 3, 5 as shown on the screen. And for fusion, we discover 3 laws, which are the cancellation law for congruence, the cancellation law for non-congruence, and the lemma on which the solvability theorem is based. And using fusion, we can take H3P puzzle as a fusion of a 5 grid and a 3-2-2 puzzle. And we can generalize this viewpoint to all rectangular MPQ puzzles as well, into which an 3-2-2 puzzle is fused at the right bottom corner. And now we can propose a new theorem to denote the solvability of a certain MPQ puzzle. If an MPQ puzzle can be rearranged, to be congruent to an alignment like this, then the original MPQ puzzle is solvable if and only if x, y, z is congruent to this n minus p, n minus p plus 1, and if your x, y, z is congruent to this, then the original puzzle is solvable, or else it is unsolvable. And by introducing solvability theorem, we have introduced a new model, what we call the river-bank model. And for short, we denote it by BRB model. And on each bank, there are the two sets of alignments, which are congruent. And the left is the solvable alignments, and the right are the unsolvable alignments. And we call those functions that does not change solvability Carr functions. And for those that do, we call them Boole functions. And here is an example of a Carr function. For example, we have 1, 2, 3, and then we use legal operations like and then we have and then we can after a Carr function we can obtain 2, 3, 1, and we write this like this. And here is an example of a Boole function. And if you reflect along the diagonal to exchange 2, 3, then we have this changes the solvability, and we call this the Boole function. And we write like this. And then we found that the number of Boole functions performed are mainly related to the solvability. And this is proved by mathematical induction in our report. And by introducing this proposition, we can propose a new algorithm to check whether certain MPQ puzzle is solvable. And we use the Carr functions and Boole functions. By using all these, we try to locate all the pieces. And if the number of Boole functions performed to locate all the pieces is an odd number, then the original puzzle is unsolvable. And the original puzzle is solvable if an even number of Boole functions are performed. And then we found that exchanges are also a kind of Boole functions as well. And this is proved by MI in our report as well. And therefore we can have an exchange algorithm in which we use the exchanges to locate all the pieces. If an odd number of exchanges are required to locate all the pieces, then the original puzzle is unsolvable, or else it is solvable. And before the illustration, we first have our conclusion first. So in conclusion, we first suggest an algorithm called the L algorithm, which we use as a tool, and then we develop the BRB model. And by BRB model, we have the Carr and Boole algorithm and the exchange algorithm. And these two algorithms help us to determine the solvability. And now it's show time for illustrating whether a certain puzzle is solvable. Okay, for example, we have a puzzle like this, and then we write the alignment like this, and then we exchange the pieces. Exchange, and then the other, and then we found that 2 exchanges are required to locate all the pieces. And as 2 is an odd number, 2 is an even number, the original given puzzle is solvable. And now we'll have, as it is solvable, we'll illustrate. Because time does not permit this. So that's the end of our presentation. Thank you.